Assalamualaikum. Very good afternoon to my student. So we shall continue our lecture today with AM modulator circuit. Okay, VSB. So VSB, yalah VSB, right? So last week
Yes,
VSB.
correct.
So
Thank you.
we are going to continue with AM modulator circuit. So AM modulator circuit, okay, amplitude relation voltage is produced by a circuit that can multiply the carrier by modulating signal and then add the carrier. So this one is the simplest terminology of how amplitude modulation can be produced. Okay, so actually EM is produced by a circuit. Okay, the resultant of multiplication between carrier and modulating signals. So product of the carrier and modulating signal can be generated by applying both signal to non-linear component such as a diode. Okay, it's a diode. And then the resultant product of carrier and modulating will produce intermodulation product, which is can consist of third, fourth, and higher order harmonic, which is generally are produced by operation of diodes and transistor. And tune circuit, which is generally we are applying some radio frequency filter, will filter out the modulating signals and carrier harmonic. So leaving only carrier and sideband lah. So maksudnya kita tahu we already apa kita sorry tak jalan kot. Okay, we know that conventional EM, so we got carrier element, we have lower sideband element and upper sideband element. But in producing EM relation will also produce a intermodulation product. So there are, for example, there are second and third harmonic signals, third port, and so on. So this one we need to eliminate the harmonic product by implementing a filter lah, a RF filter. Okay, yang ni adalah illustration, a simple illustration of EM circuit block diagram. So here is a VMT, or our modulating or information signals. Here carrier signal VC, VCT. Okay, so VCT amplitude of carrier here is varied accordingly to the VM signals by mean of multiplier here. Ini multiplier, symbol of multiplier. And then the product of multiplier will be added by carrier itself to produce a VM. So at least we need analog multiplier and we need an adder or sama lah to produce conventional amplitude modulation with V, A, and T. We can see it double sideband, full carrier lah. Okay, there are two types of amplitude modulator. Okay, the first one is low level. The low levels in terms of power needed to produce AM, and also high level modulator. So low level modulator generate EM with small signals and must be amplified before transmission. So for a low level amplitude modulator, so there is extra device which is an amplifier to boost our low level signals lah, low level power signal. High level modulator produce AM at high power level, usually in finite amplifier stage of a transmitter lah. So kat sini, kalau kita pakai high power level, of course we are dealing with with high power AM wave lah. Biasanya transmitter dia berada dekat the final amplifier stage, stage yang last kali, the end of cascaded system lah of AM transmitter. Low level amplifier, for example, there are diode modulator, the simplest one, okay. Transistor modulator using a BJT or PNP transistor, pin diode modulator, and then differential amplifier modulator. So four example of low level amplitude modulator. Okay, here is an illustration of diode modulator with tuned circuit filter. Okay, so a simple diode modulator consists of resistive mixing network. Okay, ada resistive mixing network which is R1, R2, and R3, and then we have diode rectifier here and tank circuit or LC tune circuit to create an oscillation lah. Oscillation. Carrier is applied to one input resistor, okay, and modulating signal to the output to other input resistor. So there are two input here, which is modulating signal VMT and then VCT lah. Okay, and then these signals will be added at this point, and the mixed signal will appear across R3. So here the signal will travel to diode. So what is a function of diode? Apa diode ni buat? What is the function of diode? So here, okay, here is a VMT, right? So VMT we see from this point. Here VCT we see from this point. So point 1 here, point 2 here, and 3.3 here we could see at this point lah, 3, right? So the mixed modulating signal and carrier signal. So amplitude of VMT plus amplitude of VCT will produce this kind of signal. Tambahkan. So ni tambah ni jadi ni yang macam this one tolak this one tolak this one, so kecil. So this one is the resultant of added signal between VMT and VCT. So at this point, port point here, we could see that the signal is the positive signal only appear and the negative signal is eliminated. Why? Because the diode will apa function diode sini? Apa diode ni buat? In electronic, what is function of diode? Apa diode ni buat? Okay, apa yang diode dia buat?
Allow current to flow in one direction.
Yes, correct. So allow only one direction of current. So that only the positive side appear at the point 4 and the negative side is eliminated lah. Okay. So here the LC tank circuit here will produce an oscillation accordingly to the output of diode. So kat sini dia jadi dia apa tu? The LC tank circuit akan resonate ikut amplitude dan ikut frekuensi of this point. Dia ikut. So dia akan create, dia akan completekan completekan signal lah. And then completekan signal, then produce a VAM lah, AM signals. Okay. Dan ni adalah diode modulator, which is the simplest amplitude modulator. The second modulator or low level AM modulator is using a transistor lah. Okay. So normally we are using a BJT, bipolar junction transmitter to handle low level of power lah. And then in this case, this one PNP ke NPN ni? PNP or NPN? Which one? Ni emitter, right? So emitter, base and collector lah. So ni tak salah ni PNP kot. Right, kita cek balik.
PNP.
PNP ya, PNP. Okay. Okay, transistor modulation consists also of resistive mixing network, a transistor and a LC tuned circuit. So samalah kan? Sama. So ada resistive mixing network, and then the diode is replaced by a transistor and also as a LC oscillation, LC tuned circuit. The emitter-based junction of the transistor serves as a diode and nonlinear device. So emitter-based here will function as a diode lah. So function as a diode and a nonlinear devices. Okay. So modulation and amplification occur as a base current control a larger collector current. Why larger collector current? Because the collector here, the point collector is supplied by VCC here, right? So VCC normally in transistor plus 5 volt plus 3.3 volt and some and apa lagi? 12 volt macam tu lah, dia tak besar lah. Okay. The LC tune circuit oscillate to generate the missing half of cycle. Ni sama juga. So dia sama function as diode modulator, tapi in transistor modulator, diode is replaced by a transistor. Okay. And the amplification in transistor is possible because here the base current will produce an amplification lah according to the collector current will produce an amplification effect. Okay. Okay, single transistor configured by EM by modulating the base kan. So base, collector and emitter kan. Okay. Transistor is biased into a non-linear operating region instead of acting as a linear amplifier. It combines signal that apply to its base. So VC carry signal and VMT is applied to the base of transistor. The non-linear mixing procedure produce some and different frequencies at carrier frequency. Itu ada akan produce some and different frequency lah. Means that akan produce FC, produce FM, what else? FC plus FM, FC minus FM, FC plus 2 FM and MFC plus NFM and so on lah. So many harmonic signal are produced at the carrier lah. So based on order of the resistance lah. Okay. The LC circuit is tuned to resonate at the carrier frequency and act as a high impedance at resonance. So frequency at the carrier frequency are available at the output. The frequency further away from the resonance mean that let's say for example resonance mean let's say 100 megahertz. If the frequency is further away from 100 megahertz, so the AC circuit appear as a low impedance and these products are effectively shorted out. Okay. Ini contoh let's say for example carrier signals, modulating signal or information signal, so we will produce a output at the collector terminal of transistor lah. Okay. So the other type is pin diode modulator. So pin diode modulator is actually a variable attenuator or variable resistance. So the resistance could be varied by using a diode. So variable attenuator circuit using pin diode produce AM at very high frequency, ultra high frequency and microwave frequency. Pin diodes are special type silicon junction diode designed for use at the frequencies above 100 megahertz. Okay, and then when the pin diode are forward biased, so maksudnya bila Sama juga diode macam ni, pin diode ni dia punya simbol macam ni. So bila forward bias, then the diode will be function lah, will be on. And when there are in reverse bias, then the diode will be turned off. Okay, when diode are forward bias, they operate as a variable resistor. So kat sini diode ni akan berfungsi sebagai variable resistor, which is the resistance up to this point can be changed, dia tak constant lah. And then attenuation caused by pin diode circuit varies with the amplitude of the modulating signal. So when this diode is act as a variable resistor, then of course this diode will introduce an attenuation lah. And then the attenuation or the resistance is varied according to the amplitude of the VMT. So the amplitude of the carrier tu maksudnya resistance of the pin diode, dia akan ubah dia punya resistance mengikut amplitude of the modulating signal. So the VEM akan the carrier will be, the amplitude of the carrier will be varied lah. Okay, ini contohnya lah. Okay, the pin diode are connected back to the back to back. Okay, so two pin diodes, okay, are forward biased by fixed negative voltage. Modulating signal is applied in the diodes through capacitor C1. So here is VMT, kita punya maklumat ataupun information signals. And then the modulating signal rides on the DC bias and therefore to add a substrate from it. Okay, in doing so, it varies the resistance of the pin diodes. Okay, the diode appear in series with the carrier and isolator and load. So positive modulating signal will reduce bias. Okay, the key point here, positive modulating signal will reduce the bias on the pin diode. Okay, so causing their resistance R is increased. Cause the carrier amplitude to reduce across the load, and negative side of VM will add to the forward bias, okay, causing resistance to go down. So R will be the resistance value of pin diode will be decreased, and then increasing the carrier amplitude. So here the amplification is low lah, and here the amplification is high. Sorry, it's high, and then here the amplification is low. Okay. Another example is differential amplifier or AM. The differential amplifier make excellent complete modulator because they have a high gain. Okay, the differential amplifier have a high gain. Okay. Good linearity. Linearity means that when the device has a good linearity, it can limit the harmonic distortion. Ingat harmonic distortion. So good linearity means that it can limit the harmonic distortion, and also it can achieve 100% modulated, which is M equal to 1 lah. So VM can be used as equal as carrier to produce 100% modulation. Okay, output voltage can be balanced, also referred to as differential. Okay, output taken between two collector or single-ended output taken from either collector to ground. Okay. The modulating signal is applied to the base of constant current source transistor. The modulating signal varies the emitter current and therefore the gain of the circuit. And then the output is EM lah. Okay. Okay, mostly in IC form with circuit in this figure lah. So kat IC tu dia terdiri daripada consists of at least three transistor. Three transistor. So Q1, Q2 and Q3. So Q1 and Q2 form the differential pair, whereas the Q3 is supplying a current source. Okay. So Q3 here fixed emitter current to Q1 and Q2, which is half of the current will flow to the emitter of Q1 and emitter of Q2, half maksudnya samalah. So output is developed across collector resistor R1 and resistor R2. Here R1 and R2. So output can be observed in R1 and R2 lah. Output is a function of difference between input. So V1 and V2. So V1 and V2. And then V output is depend on V1 and V2 lah. Di mana A here, A is producing or is introduced an amplification. Okay. Also the amplifier can also operate with single input. For example, one input, okay, either input is grounded or set to 0 lah. So if V1 is 0 here, output at collector Q1 equal to apa dia? Maksudnya gandaan ataupun gain of times V2 here. Ataupun if V2 is 0 here, then V1 is equal to minus A, V out is equal to minus A V1. Dia berapa tu? Phase is reverse. The direction is reverse. And the gandaan or the gain is same lah, constant. Okay. Okay, in high level modulation, the modulator varies the voltage and power in the final RF amplifier stage of the transmitter. The result is high efficiency in the RF amplifier and overall high quality performance. So high level modulator can be divided into two types lah, which is collector modulator or series modulator. Okay, collector modulator. Collector modulator is a linear power amplifier, LPA, linear power amplifier. So low-level modulating signal are amplified to a high-level power. A modulating output signal is coupled through a modulation transformer to a class C amplifier. Okay, so here the use of transformer is implemented lah. For example here, okay. So here for example, it's our voice or VMT, information signal, and then here is a carrier lah, our carrier. So our modulating signal is amplified by this device. Ada tu apa tu? Gain ataupun amplifier, high power audio amplifier here, and then will transfer to modulate the carrier which is supplied by this transistor. Collector modulator, which is collector here, collector modulator. So collector modulator supply modulate the carrier signal power here by using a secondary winding of transformer. Okay. And here the resultant product of modulating signal and carrier signal will be transferred to the secondary transformer to the secondary winding of secondary transformer before transmitting the signal to the receiver. Itu high level collector modulator. High level collector ni senang nak tahu, dia pakai will use transformer to transfer the energy lah, the power. And then we got series modulator. A series modulator produce high level modulation without a large and expensive modulation transformer used in collector modulator. So here, the high level collector modulator, we are using a transformer, but here we're not using a transformer, but still can produce high level modulator. Okay. So a series modulator replace the modulation transformer with an emitter follower. Okay, series modulator, okay, replace the modulation transformer with an emitter follower. So here kan, tadi kita nampak dia pakai transformer, yeah, right? So transformer. So the transformer here is transformer there are replaced with a series modulator, which is transistor lah. So emitter follower. The modulating signal is applied to the emitter follower. Okay, so emitter follower. The modulating signal is applied to the emitter follower. Okay. The emitter follower is in series with the collector voltage. Okay, the collector voltage change with variation in the amplified audio modulating signal lah. So kat sini dia sama je dengan apa tu dengan high level collector modulator, cuma this one dia pakai concept of transistor lah. And then still it can produce a high level of amplitude modulation. Okay. Next slide is about circuitry for DSB suppressed carrier, which is double sideband suppressed carrier, which is we can expect that the carrier element of this EM is reduced or suppressed, tak ada. So FC here tak ada. Okay. So only leave the sideband, sideband pair lah. So double sideband pair. So lower sideband and upper sideband. Okay. One approach to produce double sideband signal is to generate a regular EM signals and then filter out of the carrier. Ni paling senang lah. So means that, for example, we have a conventional double sideband full carrier, right? So double sideband full carrier, for example, FC plus FM, FC minus FM. So carrier element, upper sideband element and lower sideband element. So dia kata sini yang paling senang adalah to use a filter lah. So means that, okay, this, let's say for example, EM wave here, use filter. So filter here, let's say, apa tu? Okay, filter here, let's say for band pass bukan band pass. Band pass that's why. Band stop filter. Band stop filter. So band stop filter means that certain region of the frequency spectrum is suppressed or is eliminated. Okay, let's say we want to produce double sideband suppressed carrier, means that we want to eliminate the carrier here, right? Carrier here. So we use band stop filter. So band stop filter with this specification, okay, we only allow lower sideband and upper sideband to pass through and eliminate or suppress the carrier element here. Tu ni is theoretical procedure, theoretical hypothesis lah yang kita boleh buat. Tapi however, this is usually not a practical approach. Okay, why? Because the carrier signal is very close to the frequency to the sideband. Okay, means that, for example, here to here is very close. Let's say FM is equal to 300 Hz, kan? So it's very, very close, sangat dekat. And then, so the filter would have to be very exact. Maksudnya, filter must be, the specification of filter must be very exact, very critical and stable within time and temperature. So RF signal is actually it's not consistent or it's not constant all the time. It would be affected by a time and operating temperature lah. So maksudnya filter macam ni, in theory we can produce this kind of filter, but in practically it's very difficult. It's very complex to produce that kind of filter lah. And it must be designed to work at one frequency. Lah, maksudnya kita nak design satu frekuensi operator RF filter operating frequency designed to eliminate the carrier element lah. So the filter is very complex lah to produce. The carrier is larger than the sideband, and reducing the carrier by filtering might still leave the carrier too strong relative to this sideband. So maybe, although we use this kind of filter, but at the end, the carrier is still there. Why? Because the power of carrier is larger than the sideband. So let's say, for example, here carrier lower sideband, upper sideband. After we are going to this band stop filter, there are still carrier element appear at the output lah. So it's not a practical approach. Okay. Alright. Okay, another approach is to use a circuit that only produce sideband. For a preferred approach is using a balanced modulator. So means that we produce or we develop a circuit that that output is apa tu? Maybe produce only one sideband. One sideband. And no lower sideband. For example, this one, for example, upper sideband and carrier element. So this circuit, let's say for example, VCT, our carrier, VMT, our modulating signal, then the output produce only carrier element and upper sideband element lah, ataupun whatever circuit ataupun only produce sideband, lower sideband and upper sideband without the carrier. So we can eliminate the usage of the filter lah. Okay, this type of circuit we can apply or we can implement a balanced modulator to achieve this kind of output lah. For the perfect balanced modulator, the output is zero when either input is zero. Means that kalau tak ada VMT, the output of balanced modulator also zero. Okay, kan? Kalau VCT which is ada carrier tapi tak ada VM also zero. So it can save save a power lah, kan? Dan kita faham, we understood from previous lecture. For conventional AM, okay, so VCT is, let's say for example, okay, here, amplifier, VMT, okay, even though VMT is not supplied to the modulator, VCT is still produced at the output. So here become unmodulated carrier to be transmitted lah. Ini for conventional or AM modulator or double sideband full carrier modulator. Okay, this is contrast to regular AM where there is a carrier signal even if the modulator signal is zero. Macam saya terangkan ni lah. Okay. Okay, apa itu balanced modulator? So balanced modulator is a circuit that generates a double sideband signal. Okay. So this circuit generate a double sideband signals, suppressing. So their features. The features, one is generate a double sideband signal. Second, suppressing the carrier, and the third, leaving only the sum and different frequency at the output lah. So sebenarnya 3 dengan 1 ni berkaitan relate each other lah. Okay. So the output of balanced modulator can be further processed by filter or phase shifting circuitry to eliminate one of the sideband, resulting in a single sideband signal. So the output of balanced modulator can be further enhanced by eliminating one of the sideband. So the resultant output will produce a single sideband signals. So for example, balanced modulator includes lattice modulator. We can use IC, so 14996 integrated chip. Also the analog multiplier also can be used as a balanced modulator. So the lattice modulator consists of an input transformer and output transformer and 4 diodes connected to a bridge circuit. Okay, here is the diagram of balance ring modulator lah. Okay. For example, here kita dah pemudahkan dah. Okay. So the operation, for example, when there are positive half cycle operation of carrier, for example. So D1 and D2 are forward bias. Okay, so D1 and D2 are forward bias. So the short circuit means that the current can flow into the D1 and D2 lah. D3 and D4 are reverse bias, which is straight and open circuits. So the current from carrier signals here, right here, is divided into two. into two equally at the center tap of the input transformer. For example, is VMT lah, modulating signals, and flow opposite direction through upper and lower half of the winding. Yeah, tengok So carrier here produce, then sampai ke center tap of input transformer here, the current is splitted to the half lah. Okay, the split to half. Okay, one goes through a D1 diode, and the half of the current goes through a D2 current. So it produce magnetic field which is both equal but opposite direction to each other. Okay, so the term opposite direction means that magnetic field that produce is cancel out each other. So here carrier is suppressed. Okay, then when the carrier is suppressed, so no carrier, the modulating signal here is passed from input to the output without phase reversal. Nampak? So here the technique how the carrier is suppressed by apa? By producing a reverse magnetic field with opposite direction. So opposite direction means the magnetic field is cancel out each other at this point. So the carrier is suppressed lah. Okay, so leaving only modulating signal to be transmitted without first reversal. Okay, negative half cycle operation. So when there are negative half cycle operation of carrier signals, so tadi this one kita tengok tadi positive negative, right? Positive negative. So we said it is a positive cycle lah. So the current will flow from negative to positive light macam ni. And then this one is a negative half cycle. So the current flow will be reverse lah from here. Okay, so here D1 and D2 are reverse bias. So means that the D1 and D2 is off lah. So D1, D2 is off, leaving, and the D3 and D4 are forward bias. Means that the D3 and D4 all on or short circuit. So same procedure happen juga. So carrier current is divided equally to the both half, right? So dia pergi sini, the current flow from negative terminal of carrier signal to positive terminal of carrier signal, pergi ke center tap of output dia, dalam form output, and then the current will flow through the D4 and will flow to the D3 is splitted equally lah, both. Okay, so both current produce also magnetic field equal and opposite direction with each other. So two current merge in the second input of transformer and magnetic field is also cancel out. Okay, betul. So cancel out lah. So bila ada magnetic field, when the current is flow through a different direction each other, it produce a reverse magnetic field, and then this reverse magnetic field will cancel to each other, means that the carrier is suppressed. So carrier here is suppressed. So modulating signal, modulating signal also can pass through a input transformer and undergoes 180 degree phase reversal before reaching the output transformer. Okay, so sama konsep macam first a positive half cycle operation, but this one the modulating signal is produced with same phase. Here the modulating signal will be produced at the output signal modulating, but with 180 degree phase reversal. Okay. So here is the illustration of the operation of balance modulator tadi lah. So here VMT, modulating signal, VCT, carrier. Okay, here the illustration when the D3 and D4 is conduct, which is produce the other side of signal. Here D1 and D2 is conduct produce the other side of the signal. So at the end, at the output of output of here, output modulating output balance modulator will produce a VEMT lah, without a carrier. So carrier, no carrier here, tak ada carrier. So why tak ada carrier? Because the carrier is suppressed by opposite magnetic field for both positive half cycle and negative half cycle. Okay. Ini sama ni, you boleh baca sendirilah, sama je ni. Okay. And then one of the to create double suppressed carrier is by using a IC 1496. So the 1496 IC is versatile circuit available for communication applications. Okay, it can work at carrier frequency up to 100 MHz. Okay, and it can achieve a significant suppression about 50 to 65 dB. Okay, the IC package include a standard 14-pin dual inline 10-lead metal can. So the 1496 IC can operate as balance modulator or configured to perform as amplitude modulator, a product detector, or a synchronous detector. So here in EM modulator, we can also use IC lah. IC is 1496. So this IC can produce also, let's say input, VMT input, VCT input, can produce, can be setting to produce double sideband suppressed carrier or no carrier lah. So kat sini pun 1496 IC pun boleh kita setting, boleh kita set it as a product detector or synchronous detector as a demodulator circuit. Okay. And then analog multiplier. And analog multiplier is a type of integrated circuit IC that can be used as balance modulator. Okay. Analog multiplier are often used to generate double sideband signal. Okay, here is analog multiplier lah. Ini sama juga, dia apa tu IC kategori. We can setting this IC to produce a double sideband suppressed carrier. Tu dibaca lah. Okay. And then single sideband circuit. Okay. So single sideband circuit, just now we already review that the balance modulator can produce double sideband suppressed carrier kan. So kita tengok sini, kat sini kita dah buktikan, we already proved that the suppressed carrier can be, the carrier can be suppressed by using a balance modulator operation. Okay. The other two methods of generating single sideband signals are filter method. Okay, filter method, which is RF filter method or phasing method. So ada two techniques to further enhance our double sideband suppressed carrier to single sideband suppressed carrier. The first one is filter method. So the filter method is the simplest and most widely used. Tadi kalau kita nak pakai apa tu tadi, first tadi tu kita nak pakai apa tu, tengok ni takut you confused tadi. Ni. This one, kalau kita nak produce double sideband suppressed carrier with filter is not usually a practical approach. Tak sesuai. Kenapa? Kita pun dah terangkan, saya pun dah terangkan tadi, sebab kita perlukan satu filter atau band stop filter that will have a specific or critical behavior to eliminate the carrier only and leaving lower sideband and upper sideband to pass through lah. So we have to design a very sharp response of filter. Why? Because the bandwidth is so small lah. Sebab carrier, let's say for example carrier sini, and then kita ada apa tu upper sideband 300 Hz. So the bandwidth should be very small and very sharp. So it's not practical. In theory, it can be produced, but in practical, it will be difficult to produce lah. But in single sideband generation, the filter method can be applied. Okay, so filter method can be applied lah. Okay. The modulating signal is applied to the audio amplifier. The amplifier output is fed to one, okay, ni lah, saya terang kat sini lah, saya terang the illustration, okay. So let's say for example, okay. So here from microphone to audio amplifier and then to the balance modulator. So balance modulator here, we already proved that it can produce a double sideband suppressed carrier kan. So here when we see through a frequency analyzer, we got upper sideband and lower sideband without a carrier, tak ada carrier. Right, so double sideband suppressed carrier produced by a balanced modulator. So here we want to produce, okay, we want to produce a single sideband, okay, single sideband either lower sideband or upper sideband. Let's say for example we want upper sideband to be transmitted and eliminate the lower sideband. Okay, for example here, okay, here ni kat sini lah. So suppressed carrier, lower sideband, upper sideband. So filter response curve here, okay. Yang ni dia nak ambil upper sideband je. So upper sideband is required and lower sideband is eliminated. Okay. Okay, for example, let's say FC here is equal to berapa ni? 100, okay, 100 megahertz. Okay. And then here, let's say upper sideband from, bukan. So upper sideband here, upper sideband, okay, upper sideband here, the bandwidth start from, let's say, 100 megahertz to 110 megahertz. Okay. Megahertz. Okay. So we want to capture or to make the upper sideband pass through a system lah from sideband filter. So sideband filter here we need to design a band pass filter. So band pass filter should be operate at least let's say here lah kat sini kan. Let's say here we know that 100 megahertz to 110 megahertz. So band pass filter we should design has a cut-off frequency here maybe 90, let's say 98 megahertz. And the high cut-off frequency here is equal 112 megahertz. So we develop or we use a band pass filter to operate with the region of cut-off frequency from 98 megahertz to 112 megahertz, and then so that our upper sideband ratio is included in the passband region. Right. So other than this region is eliminated, is alternated, so that we can produce only a single sideband, which is upper sideband to be transmitted, and this signal will be amplified by a linear power amplifier before transmitting signal to the receiver lah. So this one is a filter method on producing SSB signals. And then the other one is by using a phasing method. Okay. Single sideband generating at low frequency using either one carrier, okay, one carrier and two selectable filter, the first one, or two selectable carrier and a single filter. Okay. So kat sini jap, kat sini. Okay, for example, let's say, Okay, first method is single sideband. One carrier, right? One carrier and two selectable filter. Okay, two selectable filters. Okay. So let's say, for example, here, preamplifier, okay, audio. So audio here, VMT is its frequency is 3 kilohertz, for example. And then goes to carrier a balance modulator, so BM, balance modulator. And carrier here, let's say FC is 100 kilohertz. Okay, 100 kilohertz. And then the output will go either upper sideband filter, okay, or lower sideband filter. So in this system, we can choose either to use USB element or lower sideband element to be transmitted lah. Okay, and then we have frequency translator before going to some amplification, low power amplification. The resultant output is single sideband suppressed carrier lah. So upper sideband carrier. Okay, here we can expect that the frequency at 0.1 here, that's a 0.1, this one 0.2, this one 0.3. Let's say 0.1, by using a frequency analyzer, we can produce that. Dia tak ada ni kan? Dia tak ada apa tu? Dia tak ada carrier. Right? Dia tak ada carrier, right? Tak ada carrier. Okay, tak ada carrier. So here berapa ni? So carrier tak ada. Right. So here at 0.1 produce the double sideband suppressed carrier. So double sideband suppressed carrier here FC 100 kilohertz. And then here berapa ni? 103 kilohertz for upper sideband elements. 27 kilohertz for lower sideband element. Okay, so yes, carrier is suppressed by using a balance modulator tadilah. Okay, and then we want to select either we want to transmit one upper sideband or lower sideband. Right. Let's say, for example, we want to use a upper sideband. Okay. So upper sideband, okay, let's say example, if we want upper sideband, so we use upper sideband filter lah. Upper sideband filter. So what kind of filter here? So actually, it is band pass filter. So we just develop or we using a filter that will allow only the upper sideband to pass through lah. For example, here 103. So our filter should be designed as having a cut-off frequency here, F low cut-off, F high cut-off, which is F low cut-off must be less than berapa? Less than berapa? 103 lah. Right. 103 kilohertz. F higher cut-off must be higher than 103 kilohertz. Kan? Okay. So and then, so let's say for example, F low band pass filter we design as a 101 kilohertz. high cutoff filter we design at 105 kilohertz. So our filter here should be the cutoff here should be 101 kilohertz. Here 105 kilohertz. So the upper sideband of the signal will pass through, and the other then this region will be eliminated lah, or will be attenuated. If we want to use, let's say if we want to use to use a lower sideband, we require a lower sideband element, then we use lower sideband filter. Also we use band pass filter lah. So band pass filter should cover the upper sideband frequency range. So let's say for example F low, F cutoff high, maybe we design at 95 kilohertz, right? F high cutoff filter we should design more than, sorry, ini 47. It's 145 kilohertz. Let's say 95 kilohertz, and then here 99 kilohertz. So here we design the filter that has a 99 kilohertz cutoff frequency at the high side, and at the low side, low cutoff frequency equal to 95 kilohertz. So that the other frequency range, then this band wave will be eliminated lah. So we can select upper sideband or lower sideband to pass through. Okay. And then the second one is one carrier, right? Okay. Apa tu? One carrier. One carrier. Two selectable carrier, and one filter. So one filter. So here the filter is fixed lah. The specification of the filter is fixed lah. So here modulating signal, and then balance modulator. So balance modulator ada dua lah. So ada dua carrier, and then goes to filter, frequency translator, low power amplification, NPA, and then the resultant is single sideband EM wave lah. Okay. So for example, dia carrier 1 and carrier 2 M. So M, for example, M is berapa ni? Let's say 100 kilohertz. So 100 kilohertz. Carrier 1000 kilohertz. Yeah, let's say for example 1050 kilohertz, 50 kilohertz. Okay. For example, okay. So filter here should be fixed, apa tu? Fixed characteristic lah. Artinya fixed characteristic, fixed behavior. Okay. So here let's say first, let's say A, B. Okay. Carrier A. So carrier A here when produced, when multiplied by 100 kilohertz. So here at point A, at point 1 here, so we use A, 1000 kilohertz at point 1. So point 1 will produce upper sideband and lower sideband, right? So upper sideband here berapa ni? Let's say ni 1000 kilohertz. So upper sideband should be 1 100 kilohertz upper sideband. Lower sideband is 1 ke? 900. Right. 900 kilohertz lower sideband, and there are no carrier lah, because here we are producing a double sideband suppressed carrier. Okay. So yeah, band pass characteristic here. So here band pass characteristic here. Let's say for example, okay, 900. Let's say 900 with cut off low 940 kilohertz, and then here high cut off specification is 1120 kilohertz. So by implementing this specification of the band pass filter, then which one which one the resultant output of filter? Is it upper sideband or lower sideband? Mana? Upper sideband ke lower sideband? Dua-dua. 1220. Upper sideband or lower sideband? 940. 900. Sekejap. Copy buat ni. 900 ke 950. Sekejap saya pun confuse ni. 940 1000. 9. Okay, 940 1120. Which one? Sekarang ni akan produce upper sideband lah. Right. Dekat sini lah. Betul. Right. So 940, 940 here, 940 until 112 kilohertz. So we are producing a upper sideband for carrier A. Okay, let's say for carrier B. So carrier B, for example, at point 1, we are producing lower sideband and upper sideband. Ni berapa ni? Let's say here carrier is 1050K. Okay. Here we are getting a 115 kilohertz, right? And then the lower side we are getting berapa ni? 1050 tolak 100, dia berapa? 95 kilohertz, right? Betul? Kan? Here the we are select carrier B, which has a frequency of 1050 kilohertz. So the upper sideband should be 1150 kilohertz. 1050 plus 100K, so 1150, and the lower sideband here 1050 minus 100K, so we got 940 kilohertz, 950 kilohertz. So here this signal goes to the filter, band pass filter, which has a fixed behavior, a fixed specification here. So 940 kilohertz and 1124 kilohertz for lower cutoff and high cutoff. So here the band pass filter will lie down here, right? Kat sini. Nampak dekat sini. So kat sini the filter will only allow a lower sideband to pass through lower sideband and eliminate the upper sideband part. Okay, that is a filter method, phasing single sideband generation by using a phasing method. Okay. Phasing method pula. Betul lah, phasing method. Apa ni? Ni phasing method, filter method ni. Ni filter method, right? Single sideband generation, phasing method, filter method. This one is ni filter method. Filter method. We are using a filter kan, filter technique kan. Okay. So the other technique is using a phase method. Ni phase method. This one phase method. Saya kena update saya punya ni, saya punya note ni. Phase method. This one phase method. So the phase shift method of single sideband generation appear complex but it's very effective lah. So here is a circuit diagram for generating a single sideband lah. Okay. So let's say for example modulating signal, balance modulator, we have two balance modulator. Okay. So balance modulator is supplied by VMT here, carrier modulating signal and carrier VCT. Each balance modulator has two input. So VMT and VCT with different phase, with a 90-degree phase shift for balance modulator 2. Ni balance modulator 2 for example. This one balance modulator 1. So here balance modulator 1 receive an input with no phase shift. Balance modulator 2 receive two input with 90-degree phase shift. Okay. Let's say VM, let's say VM cos 2 pi FMT. Okay. Carrier is VC cos, VC cos 2 pi FCT. Right. So in this point, let's say here A point and here B point, B point, here C point, okay, C point, A, B, C, A, B, C. So we observe the resultant output at A, B, and C point. Okay, at A point, so balance modulator VMT and VCT. So the output can be simplified as, let's say for example, cos 2 pi FMT times apa? Cos 2 pi FCT, right? Without phase reversal. So here by using a trigonometric identity, which is cos A cos B equal to cos A minus B plus cos A plus B divide by 2, right? So same terminology here. Here is cos A, here is B, for example, or AB or terbalik B, this one B or this one A pun boleh, tak ada masalah. Okay, so the resultant output will be cos 2 pi FC minus FMT plus cos 2 pi FC plus FMT divide by 2, right? By using a trigonometric identity here, right? Okay, and then here cos 2 pi FMT. So cos A plus 90 jadi berapa? Cos A ada phase shift 90 degree, so it would be a sin A. Ini dia punya identity dia lah. Right, identity. So here sin, so here should be VMT jadi cos 2, bukan cos, sin lah. Right. So jadi sin, sini jadi become sin 2 pi FMT, right? And here also cos 2 pi FCT for a carrier is having a 90 degree phase shift, then the output is sin 2 pi FCT. The resultant output at point B should be berapa? Sin 2 pi fmt times sin 2 pi fct. So tinggal berapa ni? Macam mana? So based on this identity also, sin B, sin A equal to cos A minus B minus cos A plus B divide by 2. So jadi berapa ni? So it becomes sin 2 pi FC minus FM minus cos 2 pi FC plus FMT. Sini ada T T divide by 2. Right. So we got two equation here. Point A dengan point B. So AB. So A and B is plus together at the adder here. So C at point C. So tengok at point C, at point C, cos 2 pi FC tolak FM, blah, blah, blah. So this guy plus this guy. So here same, ini sign ni cos kan, ni cos ni, sorry, ni cos. Right, ni cos kan, cos. So cos 2 pi FC minus FM. So this one pun cos 2 pi FC minus FM become cos 2 pi FC minus FM T. Right, sama lah sebab setengah half cos 2 pi FC minus FMT plus half cos 2 pi FC minus FMT, so become cos 2 pi FC minus FM. So here plus cos 2 pi FC plus FM minus minus cos 2 pi FC plus FM become 0, right? So become 0 means only leave cos 2 pi FC minus FM. So here is proof that this type of circuit will only produce a lower sideband element. So the upper sideband elements here is cancel out each other by a process of adder here. Okay. Ni faham Okay, okay kan? Okay. Kalau ada questions, you can interrupt me lah. I think we take a break for 10 minutes. It's okay?
Okay, Doktor.
Okay, alright. Kita sambung kan. Okay, EM Demodulator. EM Demodulator, first we are going to review about the demodulation of double sideband full carrier EM. So major advantage of EM is the ease of the demodulation process. So EM is not the demodulator circuit is not complex compared to other modulation technique lah, which is FM or phase phase modulation or frequency modulation. So there is no need for synchronous demodulator for double sideband full carrier. Since the message signal VMT satisfy the condition VMT less than 1, then the envelope amplitude 1 plus VMT is always more than 0 lah. Here is the diode detector and EM demodulator. So here, one positive alternation of the EM signal, the capacitor charged quickly to the peak value of pass by a diode. When the pass voltage drop to 0, the capacitor discharge into the resistor, so that it create the resultant discharge output lah. And the time constant of the capacitor and the resistor is long compared to the period of the carrier. Okay. Here diode. So diode, let's say EM signal. EM signal kita dapat macam ni kan, sini kan. Let's say EM signal. EM signal. EM signal. So let's say EM signal. So diode here allow the positive side of the signal to pass through and block or eliminate the negative side of the signals, EM signals. So the capacitor here, the capacitor and R1 here is discharged, the capacitor is discharged into R1 when the diode D1 in a reverse bias or negative cycle lah. Means that, for example, here you see, so here positive side and negative side discharge, right? And discharge, so here discharge. Negative side here discharge. Positive side ada lagi, right? And then ni positive side, negative side here discharge. Discharge tu sikit lah. Maksudnya dia akan jadi macam ni nanti. Dia akan jadi ni. Macam tu. Nampak tak? Dia macam tu. Dia create apa tu? Create a discharge voltage. Discharge voltage across the output lah. And then the original information of modulating signal should be produced at the output lah. Okay. Diode detector. So diode detector, the capacitor discharge on the slightly when diode is not conducting. The resulting waveform across the capacitor is close approximation to original modulating signals. Because the diode detector recover the envelope of the EM modulating signal, the signal is sometimes called an envelope detector. So here, diode detector waveform is detect the envelope of the EM wave. So let's say, for example, rectify EM diode here, and then the envelope detector detect the peak of the EM wave. The peak, but the detect peak of EM wave means that detect the envelope of the EM signal lah. Okay. The diode demodulator. So D1 here rectify the signal producing only positive result, and then the rectifier circuit will quickly charge C1. Masa positive side, the capacitor is charged, and when it's negative side of the EM wave, the capacitor is discharged. So the RC time constant of R1 and C1 is made long enough so that C1 does not have to discharge before the next pulse is received. So voltage across C1 follows the amplitude variation of the carrier, okay, not the carrier signal itself, okay. So finally, DC component is removed by C2. C2 is act as a filter capacitor lah, filter cap dia. Okay, we also have a transistor demodulator. So transistor demodulator, EM input is applied to Q1 base. C1 is the coupling capacitor. Okay, the function of the C1 is to block the DC component from the input EM signals. R1 and R2 establish a base bias, and R3 is established a collector bias. Transistor is a bias for class P operation that allow only positive pulse on the output. C2 function is to filter out carrier frequency, and C3 is function to remove DC component of demodulated EM wave. Synchronous detection, okay, one of the type of demodulator is the synchronous detection. The synchronous detector use an internal clock signal at the carrier frequency in the receiver to switch the EM signals off and on, producing rectification similar to that in a standard diode detector. So here for synchronous detector, internal clock signal is used to control the EM signal off and on. Okay. Okay, for double sideband or single sideband demodulation, the carrier that was suppressed at the receiver must be reinserted. So here the key element of the double sideband and single sideband demodulation, the carrier must reinserted at the receiver circuit lah. A product detector is a balanced modulator used in the receiver to recover a modulating signal. Okay. Parameter, apa itu parameter to define? To define the ability of a receiver to successfully demodulate radio signal. The first one is selectivity. What is selectivity? So the selectivity is ability of a receiver to accept a given band of frequency and reject all other. Ini type macam filter, right? So filter pun ada have their own selectivity, di mana selectivity itu akan sebenarnya selectivity itu adalah satu pengukuran ataupun ability to accept the given band of frequency dan juga reject other frequency lah. Okay, for example, by using the bandwidth of the receiver at the minus 3 dB points, okay, and tapi tak necessary to show rejection characteristic. Okay, most common use point another at minus 60 dB ratio of the two called shape factor. Ni contohnya macam ni, right? So the selectivity or shape factor is calculated by finding a bandwidth at minus 3 dB divided by bandwidth at minus 60 dB response lah. Okay. So here minus 3 dB its bandwidth from F1 to F2 kan. And then let's say for example here at minus 60 dB the bandwidth is ranged from F3 to F4. So bandwidth at 3 dB F2 3 dB ni F2 minus F1 divide by F4 minus F3 for minus 60 dB. So we get the shape factor ratio in unitless, tak ada unit lah. So shape factor. So shape factor required is apa? Kita required low lah. Low shape factor is required. Okay. One of the beside the selectivity, selectivity also is apa tu? Ni. A receiver with good selectivity will isolate the desired signal in the RF spectrum and eliminate all other signals. Okay, sama juga dengan terminology of filter, RF filter, obtained by using tune circuits. So LC circuit tuned to resonate at desired frequency. The Q of this tune determine the selectivity. Okay, Q beside shape factor, we also can represent the selectivity by mentioning a Q value. So what is a Q value? Q value is a ratio of inductive reactance XL to resistance R. So Q equal to XL over R, and its bandwidth can be calculated by dividing the response frequency to Q ratio. Okay. The second parameters to indicate the receiver performance is sensitivity. Okay, the sensitivity is the minimum RF signal that can be detected at the input of a receiver, but still produce a usable demodulated info signal. It also called a receiver threshold. Okay, the sensitivity mostly depend on the noise power at the input, noise figure, sensitivity of the EM detector, also bandwidth improvement factor of the receiver. So ada banyak apa tu? Ada banyak factor that influence the sensitivity of receiver lah. Okay. The best way to improve sensitivity is by reducing the noise level. So the noise level can be reduced by, you know that noise power can be calculated by N KTB, right? So KTB in chapter 2. K Boltzmann constant, T temperature, B is bandwidth, right? So bandwidth, temperature, Boltzmann constant. So here we know that by reducing the temperature and by reducing the bandwidth, we can reduce the noise level, thus improving the receiving noise figure. Okay. Bandwidth improvement factor. Okay, bandwidth improvement factor is one way of reducing the noise level is by reducing the bandwidth of the signals. Itulah, by reducing the bandwidth of the signal. Also by NKTB tadilah. Tadi betul NKTB to reduce the bandwidth, can also reduce the noise power. But there is a limitation for reducing the bandwidth to make sure information is not lost. Of course lah, kan. Let's say for example, kita ada bandwidth of EM, FC plus FM, FC minus FM, whereas its bandwidth is 2 times FM. Okay, when we want to reduce the noise level, make sure we did not reduce the bandwidth of the receiver sampai macam ni. So maksudnya kalau kita buat bandwidth receiver tu, it's not include the upper sideband, lower sideband, then the information will be lost. As RF bandwidth at the input of the receiver is higher than the intermediate frequency, IF bandwidth of the output of the receiver, reducing the RF bandwidth to intermediate improvement factor bandwidth ratio effectively reducing the noise figure of the receiver. So bandwidth improvement factor can be defined as bandwidth radio frequency over bandwidth intermediate frequency. So noise figure improvement expressed as 10 log BI lah. 10 log ni bandwidth improvement factor. So NF equal to 10 log BI. Example 3.8. High Q tune circuit is used to keep the bandwidth narrow to ensure that only desired signal is passed. Assume that 10 microhenry coil with resistance of 20 ohm is connected in parallel with 101 and 4 picofarad variable capacitor. The circuit resonate at what frequency? The circuit resonate at what frequency? So here we need to know the inductive reactance lah. So inductive reactance is equal to XL equal to 2 pi. Sorry, ni sekejap. Ni first requirement dia kan. First, ni second, third, fourth, fifth kan. Okay. So first the circuit resonate at what frequency? So 1 over 2 pi LC. So L, we know L is equal to 10 microhenry and C equal to 101.4 picofarad. So 1 over 2 pi root mean square of LC. So we got the response frequency equal to 5 megahertz. The second question require us to calculate the inductive reactance. So inductive reactance is XL. So 2 pi FR L. So you got 314 ohm. The third one is what is the bandwidth of the tuned circuit. So bandwidth of the tuned circuits FR equal to FR Q lah. Kita ada Q kan. Q tadi selectivity SL over R. So bandwidth can be calculated by FR over Q. So the bandwidth of this signal is 318.47 kilohertz. Okay, and then the fourth question, find the upper and lower cutoff frequency. Okay, find the upper and lower cutoff frequency. So we know that the bandwidth is equal to 318.7 kilohertz. And we know that the frequency response of carrier frequency is equal to 5 megahertz. 5 megahertz. So the upper side, the lower side and upper side of these signals can be calculated by divide 318.47 to 2. So you got 0.159 megahertz at the lower side, and the upper side 0.159 megahertz. So the upper side can be calculated by FC plus 0.59 megahertz, and the lower side can be calculated by 5 minus 0.159 megahertz. Okay. Okay, there are two types of AM receiver. Okay, tuned RF receiver, which is the simplest receiver. Limit to single channel or low frequency application. It has a high sensitivity, but the bandwidth is inconsistent. Okay, bandwidth is consistent and varies with center frequency when tuned over a wide range of input frequency. Means that selectivity is changed. And then it also not stable. Why? Because due to the large number of RF amplifier, all tuned to the same center frequency that make an oscillation. Also, the gain is not uniform over a wide range of frequency. So here is a example of tuned RF receiver. Tuned RF receiver has a cascaded amplification stage. Then ada detector, ada amplifier, and then last sekali speaker lah. Tapi dia punya disadvantage tu bandwidth not consistent. First, bandwidth tak consistent. Selectivity they change. And then it has instability issue because why? It has a multiple amplifier circuit that tune to the same carrier oscillation, carrier signal here. So dia tak stable. Okay. And then we have super-heterodyne receiver. So heterodyne means that to mix two frequencies together in a non-linear circuit, or to translate one frequency to another using non-linear device. So RF amplifier here. So we have RF section, ada mixer and converter section, intermediate frequency section, audio detector section and audio amplifier section. Okay. So RF amplifier is to provide initial gain and selectivity. Okay. And to minimize radiation of the local oscillator through the receiver antenna. Okay. So here mana tadi? Mana penting ni? Okay. Okay, converter or mixer. So converter RF is down converted to IF, intermediate frequency, but shape of the envelope remain the same. Means the info is conserved and bandwidth is unchanged. So tadi FI tadi kan. So FI here mana dah? Mixer FI in frequency. So FI here input here, F output is a local oscillator lah. So local oscillator, F input. So F input multiply or mix with local oscillator will produce apa tu? Will produce sum and cross, sum and apa tu? Sum and subtract cross product. So means that we have Fi, Fo, Fo plus Fi, Fo minus Fi or Fi minus Fo. So input and output of local oscillator. So output of the mixer infinite number of harmonic and cross product including RF, FLO, FRF plus FLO and FRF plus FLO. The local oscillator is designed so that its frequency is always below or above or below the desired RF carrier by an amount equal to intermediate frequency center frequency. Okay. FLO is usually higher than FLF. So FLO here is FRF lah. So FLO must be higher than FRF. Okay. Because up conversion leads to a smaller tuning range. Smaller ratio of the maximum to minimum tuning frequency, much easier to design an oscillator that is tunable over a smaller frequency range. In mixer and LO, if mixer and LO are in single stage, it's called converter. Kalau mixer dan LO single stage, namanya converter. Kalau dia lebih daripada single stage, it's called a mixer. Okay. So common intermediate frequency of IF is equal to 455 kHz. Adequate selectivity because it is difficult to design sharp band pass filter if the center frequency is too high. Center frequency is fixed and factory tuned, effectively suppress ACI because of its high gain. Okay, here FLO tadi for high side rejection FLO local oscillator kat sini kan, local oscillator ni local oscillator ni FRF ni IF lah, intermediate frequency. So FLO is FLO for high side rejection. FLO equal to FRF plus FIF. For low side injection, F local oscillator must be designed so that FRF minus FIF. So FLO local oscillator tadi, FRF is local operating frequency response, RF radio frequency, and FIF intermediate frequency. Okay. And then ada IF amplifier for one or more stage, provide most gain selectivity, and Demodulator is to recover the original signals. For example, we're using a detector and the audio amplifier to amplify the detected audio signal to be passed to the user. Okay. An image frequency is any frequency other than the selected radio frequency carrier that, if allowed to enter a receiver and mix with the local oscillator, will produce a cross product frequency that is equal to intermediate frequency. Okay, for example, okay. Mathematically, for high injection of the image frequency is equal to FLO plus FIF, F image, FRF plus 2 kali FIF. Okay. Ni kalau baca pun tak faham juga tengok ni. Tengok apa? Kita tengok example dia. Okay. So determine the image frequency of FIM for the standard broadcasting broadcast band receiver using for FIF equal to 455 kilohertz and tuned to station at 620 kilohertz. Yang ni FRF. 620 kilohertz. This one kita nak cari F image berapa. And then the F intermediate frequency for super-heterodyne receiver is always 455 kHz. So the first is to determine the frequency of the local oscillator. So the local oscillator minus the desired station frequency of 620 kHz should equal of the IF of 455 kHz. And then F apa tu? FIF must be equal to FLO minus betul kan? F balik. Mana tadi? FLO plus FRF plus FIF ataupun FRF minus FIF. Dah dua lah. So FLO FRF plus FIF or FLO equal to FRF minus FIF. So here this one is FRF FIF. So ni ambil ni. Kan? FLO minus 620 kHz, you got FIF. So FLO is equal to, it must be set at 1.1075 kHz. FLO, local oscillator. Now, now determine what the other frequency when mixed with 1075 kHz produce an output at 455 kHz. So X minus dengan FLO, you got 455, then the image frequency is 153 kHz. X equal to 1530 kHz frequency. So this signal is the image frequency in this situation. To solve problem associated with image frequency, sometimes the technique known as double conversion is employed. So that other than 62 kHz that produce intermediate frequency of 455 kHz, one other signal that can produce also 455 kHz image intermediate frequency is 1530 kHz. So that 1530 kHz is the image frequency in this situation lah. Okay. Image frequency rejection ratio IFRR. So it is a numerical measurement of the pre-selected ability to reject the image frequency. So the image rejection, which is alpha, is equal to 1 plus Q2 or quality factor of the tune circuit. Tadilah QFR over B, right? Multiply with rho. Rho is the rejection ratio. So the rejection ratio of the receiver can be calculated by F image over F radio frequency minus F radio frequency over F image. Ini F image. Okay. So this ratio is called the rejection ratio or rho. So here the image rejection alpha can be calculated in dB. So just 20 log alpha lah. So image frequency rejection ratio in dB. Okay, for example, calculate the image rejection in decibel, assuming the input filter consists of one tube circuit of Q of 40. So at all, we need to use this equation lah. So alpha equal to 1 plus Q2 plus row. So we need to calculate Q. Q is already given, right? So Q is equal to 40 and row here need to be calculated. So row F image over RIF minus FRF or F image. So F image in this question is 1502 kilohertz and the response frequency is 620 kilohertz. So just replace the F image and FRF, you got 2.0625 value. So you need this lah. You need yes, tadi unit. And then the alpha, the rejection ratio can be calculated by this formula. So 82.5061 in dB, just 20 log alpha. So you get 38.63 decibel. Okay. Automatic gain control. Automatic gain control, apa tu? Its function is to allow relatively constant receiver output for widely variable received signals. So the AGC helps to maintain a constant, constant output voltage level over a wide range of a RF input signal level. So for example, without automatic gain control, to not miss a weak station, you would probably blow out your speaker, while a weak station may not be auditable. Kalau maksudnya kalau tak ada AGC, sebab the power received by the receiver is not constant kan, ada turun, ada naik, So we need something to make it more stable before we process the demodulation. We start a demodulation process lah. So we need AGC to make it stable. Macam ni. Alright. Kadang-kadang datang, kadang macam ni, kadang-kadang angin kuat. Ni kan. Jadi so we need to maintain it power lah. The received signal from the tuned circuit is constantly changing as a result of changing weather and atmospheric conditions. Okay. So the AGC allow you to listen a station without monitoring the volume control lah. So example for you dengar radio, kalau tak ada AGC kadang-kadang you dengar kuat, kadang-kadang you dengar slow. Tapi with AGC we can hear a constant power of voice lah. Terdengar constant je. Okay, here is the illustration of AGC lah. So ada RF stage, antenna, ada gain tuning, which is from a local oscillator that tune at the RF stage and the mixer, AGC, intermediate amplifier and detector. Before we can hear the sound through an audio speaker. Okay, advantage of AM. So advantage of AM, very simple, attractive, simple, effective, inexpensive. Okay. AM is used in AM radio broadcast, TV aircraft, CB radio, Sideband radio, also in computer modem. Okay, so AM ni satu modulation yang konvensional. Orang tak pakai sekarang, AM ni jarang dah pakai kan. Tak pakai dah untuk sebut setting. Kecuali untuk for commercial radio, we are not use AM anymore in Malaysia. Okay. Disadvantage of AM, okay, of course, wasted power in carrier, which is not info carried, it's not efficient. Even when M is equal to 2/3 of PT is still in PC. Okay. So I think we already finished our chapter 3. Chapter 3 part 1. Chapter 3 part 1, which is an amplitude modulation. So any question? Any question?
No, doctor.
Okay. So I think we stop here, and then next week we continue with part 2 of chapter 3 which is agglomeration. Okay, so thank you very much.
Doktor, Doktor, tak dapat scan tadi, Doktor.
Tak dapat scan, sekejap. Nama apa?
Tinisian.
Definition. Okay, lagi siapa lagi?
Ya, Doktor.
Okay.
Doktor.
Ahmad Faris ada?
Saya Doktor. Saya Ahmad Haris Kamal.
Ahmad Haris.
Nombor 2.
Okay. Faris? Ahmad Faris? Tak ada? Ahmad Faris. Ahmad Faris tak ada ni. Ahmad Faris tak ada. Magdi pun tak ada. Okay. That's all. Okay, thank you very much.
Doktor, kalau nak request yang PBL tu, extend lagi seminggu boleh ke?
Doktor.
Okay, saya menjawab soalan pertama tadi lah. Untuk PBL request seminggu PBL. Seminggu, sepatutnya kan hantar bila? PBL? 27 hari bulan. 27 ni 27 hari apa 27 hari Sabtu. Okey, saya bagi sampai 1 bulan okey. Seminggu lah. Buat seminggu lah. Okey.
Thank you, Doktor.
Okey, 1 bulan 1 bulan 12. Okey. Alright. Okey. Okey, lagi apa question apa tadi?
Saya nombor 1 Dr. Ahmad Faris.
Ada. Okey, alright. So, Mahdi Muhammad, are you present today? Tak ada ni. Beria-ya cakap orang putih. Pun tak ada ni. Kita okay, we meet again next week. Okay. Thank you very much. Okay.
Thank you, sir.
Thank you, Doktor.
Thank you, Doktor.